Good morning, everyone. Good day. My name's Joshi. I'm going to be the moderator for today's panel on space qualification. Thanks again to Georgie and the other members of the Space Diversity Alliance for that awesome presentation just before. Really good job. Today, we're going to be having a quick chat about space qualification, what it means, what you need to know, and why it's important to the space industry right now. Guessing this is my clicker here. Perfect. Okay, excellent. So what is space qualification? Really briefly, it's the effort to test and prove that space systems work on Earth before we send them to space. So as close as we can get to space heritage before we can actually get it. And in a world where we don't quite have the strict rules on some qualification elements yet, really it's an effort to de-risk your mission and encourage success before you send things up to orbit. So part of that effort is the Space Qualification Network in Australia, who you may or may not have heard of. It's a collaboration between seven different institutes and facilities across the country, and all of their locations as well, all geared towards testing and proving that space systems work before we send them to space. I'll give a little bit of an overview of the way the presentation is going to work today. We're going to each go through, we've got a number of members from each of the facilities up here today. Each person is going to go through what their facility does, what they're testing, why it matters, and then at the end we're going to run through a round of questions from the audience, and I've also got a few prepared here as well. So a little bit of history about the Space Qualification Network in particular. Nova Systems was engaged by the Australian Space Agency in 2020 to take a look at the existing capabilities and facilities in Australia that can perform space qualification. Places with, ion beams, particle accelerators, thermal vacuum chambers, places like this, and see how can we incorporate all of these elements together into a cohesive space testing solution. In 2021, the Australian Space Agency actually provided funding to create the NSQN through a SIF grant, the Space Infrastructure Fund. And that was excellent because it funded the creation of a number of new capabilities within the National Space Qualification Network. And in our case for Saber, a lot of really cool modeling software that we developed as well. The NSQN has been functional now since that 2021 date. And looking forward to the future, we're looking to build out, more facilities. But I think most importantly, we're looking to build an understanding of the importance of that space qualification and get more people testing their space missions and the components of them before sending things to space. I won't go through this slide in too much detail because we're going to have everyone talking about what their different facilities do. But here's just a little overview of all the different capabilities of the different facilities that are going to be having a talk today. And then also we've got some links to the main website because we're not giving out the slides for this one, so a lot of QR codes and links so that you can take photos if you wish and you want to know more information. I'll leave that up there for a little second. Awesome. So, on to Saber's part. As I said before, my name's Joshi. I'm the mission design lead at Saber Astronautics, operating out of our Sydney office. Saber's been around for a little while. If you haven't heard of us before, we were founded in 2008 by Dr. Jason Held, and we're a mission services company. We do everything that isn't building satellites and building rockets. We operate satellites, we do space domain awareness, we do research and development for the government, and my little bit, we do mission design as well. There's some nice photos of our space mission operations facility down in Adelaide. Why is Saber involved in space qualification? Well, the first part of qualifying any space mission is qualifying the design of that space mission before you've even made any bits and bobs that need to be tested and blasted. So the part that we're involved in is modeling, taking an understanding of a space mission before it's been built and trying to recreate the radiation and environment for that space mission through software, through our simulations. The accuracy of these simulations is really important. However, a lot of the time people don't know everything about their space mission before they start building. So riding that line between high fidelity simulation and also having something which is broadly applicable to a range of different kinds of space missions before they get designed is what's important to us. Now, I'm going to do my best to explain a number of different kinds of space. We're talking about space radiation as part of qualification in this particular presentation. Of course, there are thermal elements and vibrational elements as well, but we've got a big focus on radiation today. Do my best to give an overview of some of the effects that can happen to a space mission as a result of the space environment, but you'll get a lot more detail from our fantastic panelists with PhDs and the like who are much more expert on the subject than I am. But the sun is an enormous part of the space environment for our satellites, for our space missions. There's a constant stream of particles, charged particles flowing from the sun, but the intensity and species of these particles changes depending on solar cycles and also how the sun's feeling on that particular day. So there's long-term cycles and short-term cycles as well. These manifest as ways as the wind itself, so manifesting as surface charging. You can also get aggravation of the ionosphere, which can increase drag on spacecraft. So you may remember, I think it was last year or even the year before now, when there was a big solar event and a whole bunch of Starlinks deorbited a little bit earlier than people imagined they would. That's a clear example of why space weather is a really important consideration, not just in the design of a mission, but also in ongoing operations. You also have effects that start to attach themselves to the computing elements of a space mission as well. So things known as single event upsets, where you might have a bit flip in a part of a computer that might corrupt some data. So on the design side, that manifests as lots of double, triple redundancy in your computing systems or shielding. These are all things that you need to know in the design of your mission, or potentially even in the design of your orbit, wanting to adjust the orbit or architecture of a mission to avoid space radiation and environmental effects. So what we did as part of this effort in radiation and space qualification is we developed a number of solar particle models using generative adversarial networks to create like a machine learning model to create accurate representations of solar weather and solar particle streams for a range of different solar behaviors. So given the sunspot number, the size of the sunspots, where we are in the solar cycle, you can get an accurate simulation of a solar particle stream, which was pretty cool. And we actually took this work and rolled it into our mission design and analysis toolkit shortly afterwards, which is our newest range of products to assist people with intuitive early phase space mission design, taking a bigger focus on the concepts before the mission rather than the satellite design itself. So allowing people to design high-level architectures with a degree of fidelity that isn't normally offered, and without having to know too much about your mission before you can start designing these kinds of things. We've really enjoyed so far all the work we've done with the National Space Qualification Network. We're really keen to do more in the future. There's us and a bunch of our interns also visiting the Centre for Accelerator Science at ANSTO in New South Wales. So we love collaborating with all of our partners at NSQN, and we hope that we can build out some more software systems and modelling systems that can assist. The next step for us in the future is trying to build out repeatable ways of translating space mission requirements into space testing requirements to make all of these folks' lives a little bit easier. But thank you for listening. I'm going to hand over now to Mike to talk about NOVA and their role in space qualification.
Thanks, Josh. Okay, so I'd like to broaden things a little bit. We're here to talk about qualification, but qualification is just one aspect of getting a space mission to work. If I can get my clicker to work. Okay, so mission assurance. NOVA Systems is a systems engineering house that has been expanding into the space arena, and we are looking at and have been providing mission assurance services. It's very important to understand how to go about developing a mission and the steps involved in making sure that mission works correctly. My apologies, I can't really read the text, it's too small, but basically the first step from a systems engineering perspective is understand what you're trying to do. Understand what you're trying to do and how you're going to do it. And then look at how you're going to operate it, because the ConOps feeds back into the user requirements, and that feeds back into getting the overall system requirements right. And of course, underpinning all of this is the available budget, the available schedule, and your risk appetite, as I've heard it discussed. Risk appetite to me is I don't like that term. It's a question of balancing the risk against all of the other mission objectives. So think of it as a table. You've got 4 legs. You've got your cost, you've got your quality or your performance, you've got your schedule, and you've got risk. And if you cut out one of those legs, the table falls over. So you always have to balance everything to be able to have a successful mission. You need to plan the overall approach, work out how you're going to do it, and then you've got to execute that plan and monitor the execution so that you're always one step ahead, being proactive of what can go wrong, how am I going to deal with it before it happens. Okay, Josh has already talked about the space environment, some aspects. You've got to design for the space environment. You have to understand the space environment to be able to design for it. I've had people come to me and say, I want to qualify my PC board for space. And I've asked them, have you designed it to work in space? And it's no, but I want to qualify it for space. Okay, fundamental misunderstanding. If it hasn't been designed to operate in the space environment, it generally won't operate in the space environment. There are a number or a wealth of information in the NASA and ESA standards. You don't need to follow them, but you need to understand them to be able to understand which are the important things that you need to look at when you're doing a mission. And also, you've got to design the entire mission. It's not just a platform. It's not just a payload. You have to look at the overall system. And I'm being spacecraft-centric here, spacecraft mission-centric, but this applies to everything, whether it's terrestrial instrumentation, whether it's a spacecraft or whether it's a lunar rover. It's everything is a system of systems that you have to understand all aspects of it, and you have to design in the capability for all the different subsystems to talk together. You've got design for the operating environment we've already discussed, and design the verification. Plan your test program early. Verification is the part of the qualification of the hardware, but you're not just qualifying the hardware, you need to validate the overall functionality of the system. The next is, okay, you've got your planning, you know how you're going to do it, you're trying to realise the hardware. Build the right thing and build it well, okay? That's fundamental. I've seen, again, a number of people fall over in this area. Having appropriate documentation and records, the right amount is important. I've got the term there, add value, not bureaucracy, okay? And that's a fundamental thing. You've got, from one extreme of the space, the old space, call it old spaces, failure is not an option. And you've got new space, which I've heard the terms rapid, risk appetite, etc., but it can also lead to fail fast, fail often. And I've seen that happen. So it's a matter of getting the right level of documentation so that you can do things in an organised manner, in a systematic manner, and not only that, you'll have the records to be able to look back through. If there is an anomaly, you'll be able to understand how it got there. 1 minute. Okay, moving very quickly. You can all read. Getting the right AIT mentality is important, getting the right team, getting the right tools. So management, I've had many fights with management trying to get the right tool to do the job. Sometimes I've been successful. When I haven't, it's been a hard life. Qualifying the hardware design. Okay, we're getting there. Space qualification is qualifying the design with margin that will work in the environment. These tests that we'll be discussing, the radiation testing, vibration, TVAC testing, they're all expensive tests to do in terms of logistics, in terms of schedule, in terms of cost. You need to prepare for them in advance to make sure that you get the best value out of those. At the end, you need to validate your end-to-end functionality, and this is critical. Many people have failed over the last 10 or 15 years in the CubeSat community by not even testing whether their spacecraft will communicate with their ground station. Do your end-to-end testing as soon as you can, and expand that to include operational rehearsals, how you're going to operate, again, spacecraft-centric, how are you going to operate that spacecraft in orbit? Do you have your procedures? Have you validated them all? And finally, the launch, getting your spacecraft to the launch facility is another logistical exercise. Needs to be planned, needs to be understood. To get it done right, it requires, in my view, a reconnaissance to understand what you expect when you get there, so that you can bring the appropriate tools, equipment that you need to deliver your spacecraft or item flight ready. And that's it for me. Thank you.
Thanks, Mike. So my name is Stefania. I'm the space radiation expert at ANSTO. ANSTO is the Australian Nuclear Science and Technology Organization. And while my colleagues already introduced the challenge of space radiation, it's very important, yes, to remind ourselves that modeling and simulating is the first step towards understanding where we're going in space. But I believe that ultimately, the answer that you're going to get is when you do a ground-based test. And this is why at NSKN we have all this facility that allows you to access space on Earth and simulates all these particles that you can find on accelerator-based facilities, and allows you as well to have an understanding of what's the probability of failure of your devices, especially when we're seeing the new space that Mike introduced, a new space that is using commercial off-the-shelves, which are not designed for space, but that we want to use to reduce the cost and to make space more accessible. So yes, radiation testing, like any other testing, is an investment, is expensive, but again, it's the way to de-risk your mission. So at ANSTO, I would like to give you a little bit of a slideshow of what we do, which type of test, and where to go. It's a little bit of a big organization. We have 2 campuses, one in Sydney and one in Melbourne. We can do clearly a perfect recreation of the cocktail of particles that you have in space. And we can do the typical type of testing that you might look in the standards. So we're talking about total ionizing dose testing when we use gamma rays generated by cobalt-60 sources, for instance, at our Guthrie facility. The reason why we do TID is because we want to investigate the cumulative effect of long exposure of our components. So it's effect that manifest when the component is experiencing radiation for longer days until we reach probably a total failure. Our facilities is split in 2. If we have like big system, big components, we can use a bunker where we have a 1 meter square homogeneous irradiation source. Otherwise, we have a gamma cells, which is a self-contained irradiator where you can place a single, simple components and you can irradiate them isotropically. At Australia Synchrotron, for a more focused and localized total ionizing dose testing, we have high-intensity X-ray beams. The idea is to use high fluxes localized on microregion inside your component to target specific sensitive region inside your devices. This is also a very beneficial testing because it's non-destructive and allows you as well to have a 2D and 3D imaging of the IC structure inside the component itself. And the second part of testing that you might see in the standard is the single event effects testing. In this case, we move to the Center for Accelerator Science at the Sydney campus, where we can offer protons and heavy ions beam to target, again, subcomponent region, component, and also small board level testing. Additionally to the single event effects, we have displaced damage, which is more suitable for materials than electronics. However, what we can do with our beams created by 2 particles accelerators, we can cover a wide range of LET and fluxes influences, which are typical of the mission that most likely Saber would design and model for you. The beams as well have this unique feature to be able to be focused down to 1 micron. 1 micron spot can target single transistors inside your device and can map the sensitivity of your IC. We have different scanning modality that allows you as well to cover on a broad beam the area of your entire device or of your small boards. We can perform irradiation in vacuum and in ambient to allow you an easy connection with your readout system. In addition to our primary facilities, we also have supplementary capabilities that offers you an end-to-end service to tailor the solution for your requests. We have indeed a decapsulation facility in-house to maximize the exposure of your device and to maximize the LET that we want to deliver of your sensitive regions. We can perform as well microstructure analysis, meaning we can identify the layers and the structure, the metallization, passivation that you can see on some electronics component. And thanks to these microstructure analysis, we can also perform Geant4 Monte Carlo simulation to model the propagation of your radiation inside the sample and have a precise determination of the LET in the sensitive region. And then, yes, we're talking about device and system, but we also have to care about humans in space and food and plants and water. So we have also radiobiology capabilities to investigate the effects on organic samples. And we also provide labs and facilities that allows you with the pre and post irradiation handling of such. Thank you.
Thanks, Stefania. Space is not empty. It is full of surprises, and we need to be ready. Good morning, everyone. My name is Sandra, and I work with the Heavy Ion Accelerators. The Heavy Ion Accelerators is a network of particle accelerators within Australia. It has 3 nodes: the Heavy Ion Accelerator Facility, the Ion Implantation Lab, both of which are at the ANU, and the 3rd node, which is at the Uni of Melbourne. I work at the Heavy Ion Accelerator Facility. Sorry. And this is what the cross-section of our facility looks like. HIAF was established in the 1970s to support nuclear physics research at the Department of Nuclear Physics using this 14 UD Pelletron accelerator. Over the past 5 decades, HIAF has evolved into a national facility that helps academic and industry users in fields such as quantum computing, detection of critical minerals, dark matter studies, and now space radiation testing. We have 11 beamlines that you see marked as end stations. And we have a 6 million volt Linac superconducting booster. I work primarily on this highlighted beamline that's called the space irradiation beamline. So we use the space irradiation beamline to emulate space-like radiation environment on Earth. So I spend a lot of my time blasting things with particles so that our satellites don't get blasted in space. So thanks to the Australian Space Agency and NSQN, we now have a shiny beamline, which was officially inaugurated 2 years ago. We zap things in 3 different stages: rastering stage, dosimetry stage, and the irradiation stage. So in the rastering stage, we have an electromagnet that helps to raster the beam on the surface of your sample. In the dosimetry stage, we use a silicon photomultiplier detector to count the number of particles in your beam. And in the irradiation stage, it consists of an irradiation vacuum chamber. The vacuum chamber consists of 2 kinds of sample mounts, one for device or electronics testing, and one for materials testing. So the mount for device testing acts like a pin board. It has 25 millimeter grid spacing, and it has an overall area of 220 by 270 millimeters. This is the materials testing sample mount. It can hold up to 15 samples that have an area of 20 by 20 millimeters. So overall, our stage is translatable in the XY direction, and it is remotely controlled. We can also tilt the stage to change the beam incident angle. And this is a list of beam species and energies that we can provide at our facility. So we can produce protons up to 28 mega electron volts till gold up to around 300 mega electron volts, and almost everything in between. The range of fluxes that we can provide is from 10 to 10 to the power 12 ions per centimeter square per second. Here is a QR code if you want to know more about our facility, but unfortunately it's not working. So if you would like to know more, or if you'd like to have a tour of the facility, please do get in touch with me, and I'll be happy to share more about the kind of work that you do. Also, I promise that our beamline is much more cooler than what I've shown you in the presentation. Thank you so much for your time and attention.
Thanks very much. My name is Mike Lerch, and I'm from the University of Wollongong, from the Centre for Medical Radiation Physics. And I'd just like to do a straw poll. Who's put something in space before? A few people. Excellent. So it'll determine how I pitch my talk. So I'm going to be talking about our single event effects laser facility and our capability at the University of Wollongong. So as the title implies, I'm from the Centre for Medical Radiation Physics, so we tend to focus a bit more on the medical side of radiation. But space medicine is obviously a very important component, and so we worked with NASA and ESA putting our sensors in space, and our sensors are particularly semiconductor sensors, so semiconductor detectors, to measure the radiation environment, to try and predict the radiobiological effect of the radiation environment in space. So I'm going to be speaking very briefly about our facility, but happy to take questions later on or talk to anybody. So I don't have a laser pointer, do I? Oh, there we go. You can see here, basically, we've got one of our semiconductor sensors. We can look at the radiation environment and measure that, but you can see here an image of a couple of tracks here from cosmic events, cosmic ray events, and you can see not only is a qualitative picture of what's going on as the particle traverses through the detector, but to get a quantitative measure of how much energy is being deposited per unit length inside the detector itself. And so this is down to a pixel resolution of about 50 microns, that we can see how much energy is deposited. And so anything in space is obviously going to be exposed to this sort of radiation environment, including ourselves if we're ever going in space, but certainly all the electronics and things like that. So we focus very much on quantifying how much energy is deposited and what is the impact that's going to have on our semiconductor devices or our electronic systems that are in space. And so for this particular event, you can see here that along the track, there's certainly energy being deposited. One track is quite distinct from the other in the sense that at the end of the track you get a massive explosion, if you like, so a huge deposition of energy inside your device, and if that happens inside a critical area of your device, then you can get these single event effects or latch-up events and things like this, which can be catastrophic to your whole mission. So it's important to know what the probability and what the impact of these such events are going to be. The laser facility itself, you can see here, so we use lasers to emulate these sorts of events happening inside your electronics, and so these are the characteristics that make us able to do this huge range of energy events. You saw those tracks where a particle is traversing and not depositing very much energy, and then you get at the end of the track where it deposits a lot of energy. So we need quite a bit of flexibility in our laser facility at the university. And so we do that by adjusting the wavelength. You can see it's tunable wavelength, where it's stable, of course, so we know exactly what wavelength it is, but we can also accelerate time, if you like. We don't want to be sitting there for days, months, weeks, years. We want to do it very quickly, and so we can have this event rate going from a single event up to 3 megahertz, and so we can accelerate time in that sense. So the amount of energy that we deposit inside our device is adjustable, and you can see there, basically. So in terms of nanojoules, so 0.01 nanojoules up to 30 nanojoules, and we can put that in a very, very small spot, of course, so the focus spot is around about a micron, and so then we can raster scan that micron spot on a single element, if you like, and then focus on that element to see how susceptible it is. We can certainly, you can talk in terms of power. We can see the area that we can go up to, so 50 by 50 square millimetres, so a reasonably substantial printed circuit board is what we can do at any one moment. And then our scanning resolution, of course, is 0.1 micron, and so we can do things very, very precisely. We do obviously have a lot of training and educational services, so we'll be providing these services regularly, and we run workshops in space qualification, and so we do that regularly, and we'll be having one next year. And so the biggest thing we need to do is qualify, benchmark our system, so we've done that there on the right-hand side. You can see the graph here, so we've a standard device that is recognised around the world. We have benchmarked our system with the other systems around the world, and so you'll know that the data you get is very, very much relevant to the data that can be obtained anywhere in the world. So this is from the University of Saskatchewan in Canada, of course, with their laser system. So it's working extremely nicely. And then on top of that, we know about the radiation environment. We work with our partners now. So once we've done with the laser, then we can then do some more intensive testing with the heavy ion beams at ANSTO or ANU. But here we can talk about the radiation transport simulation, since that's the other important component of our work. That the radiation environment, you have what radiation, the primary radiation environment you're in. You're interested in the secondary and the tertiary radiation environment. So here we're trying to develop new models to put in GR4 to measure direct and indirect damage. So you've got the physical damage, and then you've got the chemical damage, if you're talking about humans anyway, or other animals and things like this that are in space radiation environments. So there's a lot of work going on in that area to develop those models further. And so this is some of our work. You can see here, measuring in cooperation with ANSTO, measuring, looking at the DNA damage done using gamma H2AX, basically looking at what's happening when we are doing that and comparing with our simulations in the GR4. So we're getting very nice data there. And I think that did for me. Yes, thank you.
So, good morning to everybody. I am Eduardo Trifoni. I am the director of the Space Test Program and head of the National Space Test Facility, which is located in Canberra, in Mount Stromlo, and is managed by the Australian National University. So, the National Space Test Facility is providing experimental activities for qualification of spacecraft, payloads, subsystem components, and definitely we are the only node and the foundation node of the NSQN for space environmental testing. So we do thermal vacuum testing, vibration testing, pyroshock testing, but also we are able to perform atomic oxygen testing and electromagnetic compatibility testing. And we have some capabilities also for measuring center of gravity, moment of inertia, and we have a large clean room for assembly and integration activities. But instead of giving you, let's say, an idea of all these capabilities, we thought it was more interesting to show you a mission case, which is the Cainini mission that we did perform the space environmental testing at the National Space Test Facility. So, no, it's this way. Yeah, the big one. Easy. So, Cainini mission is an example of a very well prepared test campaign, and here you can see here you can see the spacecraft, the Cainini spacecraft inside our thermal vacuum chamber. This is the actual flight unit, the one that is actually in orbit. It's been developed by our partners Inovor, Myriota, and SmartSat CRC. Some of them are here present in the room. And good morning. And so this is the plot of our facility data inside the thermal vacuum chamber. And so basically you can see there the temperature of the shroud and the platen of our chamber. So we are not providing you data about the spacecraft for obvious reason. And just to show you how a thermal vacuum testing is going ahead typically. So when you are speaking about thermal vacuum testing, you want to submit the spacecraft to the same condition that you expect there will be in space. And so does it mean vacuum, and so the absence of the atmosphere, and also the temperature that the spacecraft will need to withstand. And so typically you have to have, first of all, a prediction of what are the maximum or minimum predicted temperature of the spacecraft. And for this specific spacecraft, it is a proto-qualification testing. So we are testing the flight unit for the first time, and before sending to space, you have to add the margin to this maximum and minimum temperature, which is typically in the order of plus minus 10 degrees. So once you have this data, you are submitting the spacecraft to the thermal vacuum testing inside the chamber. And for this specific testing, we did perform in the first day the bake out. So basically, we heated up the spacecraft in vacuum condition to let him outgas. And so this first day of testing was devoted to this scope. In the second day of testing, instead, we did the first thermal cycle, and so we heated up the spacecraft, and then we cooled it down during the same day, and keeping in this hot and then cold condition for a few hours to check if everything was working. So at the same time, the team did several functional testing while in hot condition and then in cold condition. In the third day, we do the second thermal cycle, same profile, just, of course, the team did additional functional testing. And then again, a third thermal cycle, and finally a fourth thermal cycle. But at the end of that day, the test continued over the night with what we call a thermal balance testing. And so in a thermal balance testing, we are submitting the shroud to the very cold condition, and then typically of the deep space. So in this case, we brought the shroud to close to minus 140 degrees Celsius, whereas the Platon was simulating the albedo condition, and so was much hotter than that. At the same time, to keep the test going, we have to ignite an infrared panel to simulate the heat flux coming from the sun. It is interesting to show you also an infrared picture that we took during this testing. And the National Space Test Facility is one of the very few facilities in the world having this system capable to measuring temperature in vacuum condition. Another thing we would like to show you is the vibration testing we did on the Canini. So it was a random vibration testing, and in this case, is the same actual flight unit inside the pod, and we shake it in the 3 direction. And you see here the plot of the random vibration testing with all the accelerators that are inside the spacecraft and on the pod. This is simulating the phase in which a spacecraft is launched into space, and so the rocket is providing very huge vibration, and we need to check if the spacecraft is able to withstand to such environment. So there are many, many details about this kind of testing. We also performed for Canini a center of gravity measurement that we are not showing here. And so there are a lot of complexities, and so we are going to speak about in the panel later, but it's something that you need absolutely to prepare of, and you need to do if you want to have a mission success. Thank you.
Good morning, everyone. My name's Andrew Guidi, so I work for Nova Systems. I feel like I'm a little bit of the odd person out on this panel here because I'm going to talk about a bit of a capability today that we're involved in that's a bit outside the NSQN. And I'll also discuss not so much space qualification testing on the space segment side, but some of the work that we've done on the ground segment side. Obviously, you know, for any space mission, you need to have a ground segment. And in some ways, you know, qualification of that segment as well is just as important as some of the work that you do on the space segment side. Sorry, just go to the... All right, so one of my roles at Nova is I look after the Nova Systems Space Precinct, which is located in Peterborough, about 3 hours north of Adelaide. We host a number of ground stations for international and Australian clients. One particular use case that I like to talk about today is some of the space testing, well, ground segment testing work that we did to support the Spirit mission. So the Spirit satellite, which was the first ASA-funded satellite, was launched in December 2023. We commenced automated operations of that ground segment on the 4th of December. So we've been supporting that for the last 18 months now. And I've got some stats there. You know, since about the 5th of June this year, we've supported about 2,508 passes. In total, we've had about 6 missed passes. So effectively, we've had a terminal uptime of about 99.95%. Downtime, as you can see there, about 4 hours per year. Some of that downtime hasn't been a result of anything that's gone wrong with the terminal or anything like that. The nature of our ground segment is that we need to do, for example, patching. Our ISP provider at times, they need to do some network patching as well. From that point of view, you know, we've got multiple customers there. There's probably not an ideal time. Someone unfortunately has to take the hit, and sometimes it's actually been Spirit that's missed out in that case there. And we operate in the band from 395 to 405 megahertz. So while there's been a lot of work that's been done, obviously Spirit over a number of years in terms of the spacecraft itself, in the background, you know, Nova Systems, we've been responsible for the UHF ground segment, and just some of the key factors that I'd like to talk about in rolling out the ground segment that we did to support Spirit. You know, some of the key points, key takeaways I'd like to say is that, you know, we did a lot of component level analysis for some of the key components that went into the Spirit ground segment. We operate around about the 400 megahertz band. There's a lot of amateur radio that operates in that band as well. You know, given some of our constraints in terms of budget and all that, we did reach out to some of the amateur radio manufacturers to provide us with components. Some of those aren't really to the level that you expect from large, you know, industrial type, defence type component producers from that point of view. So the key takeaway is that, you know, we needed to do unit testing on every single unit that came in to make sure that it actually met its actual specifications. And the bottom line is, don't trust the specification sheets, what someone put down on a piece of paper from some of these manufacturers. Another key element of the way that we put Spirit together was that we had an iterative integration process. So, you know, when we build up the transmit and receive chains, we put together certain elements of, say, the transmit chain. We tested that. We made sure we shook out any problems there before we looked at integrating further elements within those chains there, so we could identify any problems early on. We also had a big operational focus testing from that point of view as well. We obviously simulated our system always with you know, the signal levels that we expected from our link budgets for what was being put down by the Spirit satellite. We also had a strong focus on remote control operations as well. Peterborough is a remote site, so we needed to make sure that if anything happened to the terminal itself, we could quickly get in there, remote into the terminal, and actually diagnose the problems remotely. We do have local support in Peterborough as well, but we needed to make sure that that level of control, the M&C for that level of control, was well understood. I can't put enough emphasis on the amount of testing that we did. You know, there was a lot of reputation there as well, with Innovol being, this is the first platform they put into space. So we felt the pressure to make sure that everything went well from the ground segment side. So we tested with multiple RF sources. You know, we used UHF satellites wherever we could. They were transmitting within our band, picking up those signals there, weather balloons as well. We also did a lot of testing on site with an engineering model of the platform itself and all the comms gear. With the Innovol team, they came out and they made sure that, you know, we did a lot of testing, you know, even wireless testing on site from that point of view. All this happened, you know, with a close working relationship between Innovol and Nova Systems and all that. So as we can see, it's still going, it's still up there, and we're still providing great support to that Spirit mission. Thank you.
Thank you so much, everyone. We're going to jump into question time now, but before we do, quick round of applause for cramming so much information into their 5-minute slots. Everyone did an amazing job. So before we jump into audience questions, I've got one just to get us started. One of the hardest parts of space qualification is translating its importance to people. What are some of the biggest misunderstandings you feel are present in industry when it comes to space qualification? And this is to anyone who wants to take it, or the whole panel.
Yeah, yes.
I think I continue to see some situation in which people continue to take shortcuts, and so avoiding simply space qualification testing. And I don't know, this is really detrimental for the mission success, and maybe these space qualification testing were not scheduled at the beginning of the project, and so there are no more time, and sometimes there are no more funding. But this is a very big issue for the mission success, because if you don't test on ground, there is very little possibility things will work very well in space then.
Anyone else want to grab that one as well?
Yeah, I'll grab it. So my background is I've been in big space for many years, and then I've been part of the Space 2.0 for the last, 15 years here in Australia. And I think the big thing is there's a lot of startups and SMEs that want to get into space, but there hasn't been enough of a core understanding of what it takes to build space hardware. And a lot of the university, the CubeSats are DOA, because again, the focus is on, look, let's get our spacecraft to work functionally, put it together. They're always running late, they're always running out of money, and then the last thing they do is well, we've got to do a vibe test in fact it's vibe to get on a launch. You have to pass a vibe to show the launch vehicle authority that you're not going to fall apart and damage anybody. Vibe is not that hard to pass, although I've seen CubeSats fail vibe with loose screws, etc. But then thermal is a major issue, and thermal testing requires an understanding of the thermal performance and thermal design, and it's also a very expensive test to undertake, and generally the organisations don't have the money or the time to be able to undertake that test. It gets to orbit, and if it works for a while, it fails very shortly afterwards. So again, it's understanding. I think I tried to cover it in my talk, is adopting a systems engineering approach, trying to understand a bit of everything. You don't need to be an expert in everything, but where there is a lack of knowledge, reach out. There are a lot of people, some sitting in this room that I'm looking at, that have a wealth of experience, and I'm sure they're all very happy to help out startups and getting to understand what you need to know, I suppose.
Awesome. I'll chuck in my 2 cents, which is what we've noticed in the mission design lifecycle with the clients we've worked with. A lot of people start to think about qualification. They're expecting to think about it at the end of the mission design lifecycle, right when the thing's already built, then we'll qualify it. I think there needs to be a bigger shift towards considering all of those factors and how you're going to be testing it right from the beginning and from the outset of that mission design lifecycle, because that's how you're going to close your validation loop. Now we'll toss it to the audience if anyone's got some questions they want to ask about the facilities. Yeah, I don't know if we're doing a roving mic situation or not. Yeah.
So with the Nova presentation, you also mentioned that there was regulatory consideration, and we found that a lot of companies also don't consider the regulatory space until way after that. Can you talk about how you work with companies with qualifications and how they look at that regulatory consideration?
Okay, so that's not my area of expertise, but I do understand. So one key thing is the Defence Export Control Act. One cannot just start sending information overseas or receive information overseas without Defence approval. And Defence have been very lenient of late, but I think they're going to start really getting serious. So getting your defence export control documentation in place for both intangibles, that's information, and also for tangibles, that's hardware export, needs to be done. Similarly with the Space Agency, you need your launch permits. Again, that takes a while. I'm not sure how long it takes now, but that's something you need to plan earlier on. Also, the communications. If you've got a spacecraft, you need to have the communications band approved. So ACMA needs to approve that, and that's a long process. So they're just 3 aspects that I'm aware of. Nova does provide that as a service for all three of those areas if required. Certainly, we've worked with a number of these SMEs in Australia on the frequency management side of things.
Awesome, thank you for that answer. Anyone got some more questions? I've got a...
Hello, my name is Jeet. I'm from University of South Australia, and I work on fabricating titanium components using additive manufacturing for aerospace applications. One of the issues is to understand what kind of tests we have to do. Is there any standard developed by ASTM or NASA or ESA that gives me some kind of understanding on what kind of tests we need to do on structural components?
I believe so. I think recently I came across a NASA standard for qualification of 3D additive manufacturing components. So I'm not 100% sure, but because it's been around for a while and people are definitely starting to use additive manufacturing at scale for launch vehicles, etc., I'd say that it does exist. So look at the NASA standards, just do a search. Also ECSS, yeah, the European standards. I'm not sure it exists, but personally I find the ECSS a lot easier to understand than the convoluted NASA standards. So I'm always pushing people to ECSS first.
We've got a question up there.
And I can put you in touch with the Gravitas people too from Wollongong, so they do similar sorts of things, so they can bring you up to speed on that sort of stuff as well.
And just to conclude, I think as well the NSQN is a place where to go. If you have such question, you have like a pool of experts in different fields and testing capabilities. So if you come to the NSQN and explain in details what's your question, what's your main goal, I'm sure that among us you will find at least some answers.
Hi, AD James from Uni SA. So G, we'll have a talk about this at some point, but I did have a question. A lot of the testing from the facilities and the NSQN is around that radiation hardening, and it's like at the component level or the subsystem level rather than perhaps the spacecraft level. So it's unlikely that a small spacecraft manufacturer will come in and do a full test of all their circuit boards. So having these facilities now, and they've been up and running for a couple of years and you've been doing some good work, I just wondered if you've seen that has encouraged any local manufacturers of subsystems or spacecraft components to come and qualify their equipment sort of pre-sales, as it were, because a lot of people are relying on costs anyway. So I just wondered if you'd actually seen any increase in traffic in that area.
Yes, maybe I can start with that. Clearly, there is an increase of requests for testing. We see it from startups, SMEs, even to more like complex and established companies. The idea is, yes, what we have to offer is from a subcomponent level testing to a component to a board, and then we can get to a system if it fits our chamber. Let's put it this way. But clearly, if we're talking about like a satellite testing, in Australia, we don't have yet such facility. I think there's really just a couple in the world where you can perform the final test. But what we always try to educate, we don't go straight to the satellites. We go from the components and then we build up the puzzle.
Yeah, they certainly have the game pond up there at ANSTO, which they can use on larger CubeSats and things like this. But I think to answer your question, yeah, there's certainly a lot of interest in doing this sort of work. The problem is we would like to help the industry, the emerging industry as well, okay, so we've got to work together. So I suppose it's, we're interested in just taking components that are regularly used. If people are willing to share what components they are, then we can just do this testing and do a suite of testing on these components to build up a database of these sorts of things, you see. But we've got to get the funding to do that as well. That's the other thing. You can't just do it for free, unfortunately, as much as we'd like to. But so that's one thing we're certainly trying to do.
I actually want to take questions in a different direction. We've got 5 minutes left, but I wanted to emphasise that space qualification isn't just an Australian problem; it's a global problem. And what do each of you think what's a unique offering that Australia presents to our region and to the world when it comes to space qualification?
So I think from my perspective, even though I'm pretty juvenile in this, I've been in this position only for the past 1.5 years, but I think accessibility is something that we have, which not many places have. So it's like I can talk about hire. So if you are completely ready, you have your sampler, let's say you have your electronics component, and you know whatever doses or LETs that you want, we can even do the testing next month if our people are available. So I think accessibility is to our facilities, and also I think pricing compared to the US. I know it's not cheap, but it's just a fraction of what you would have to pay in the US. So I think accessibility and cost are two plus points that we have in Australia.
And can I just quickly jump in? Just again, I'm talking from the ground segment perspective. What we find with Peterborough is like some of our clients that we've got out there, they've come to Australia. I've asked them, they like the stability that we have in Australia. So whether we've all got personal opinions, but we do have relatively stable government, stable economy here in Australia. From our side, again, we do a lot of work. Say, for example, with Terran Orbital, they fly a lot of experimental NASA payloads. They like the certainty that we have in Australia here in terms of the licensing that we can provide, the ACMA licensing. It's fairly black and white what you can do from that perspective. So they appreciate that. They appreciate the fact that in Australia we do have relatively stable power sources, internet sources with good access of dark fibre. So I think it's a combination of that ecosystem there, which from the ground segment perspective, we have a unique offering here in Australia.
And finally, our ability to innovate. I think Australians in general, going right back to our First Nations people, incredible in terms of survival instinct. And for all of us, it's ingrained in our DNA to come to another country and establish a life and everything like that. It takes an incredible amount of innovation to be able to think like that, and I think it's part of all of us in Australia, so we're all very innovative.
Awesome, thanks for those answers. I think it's super important for everyone to know how unique this sort of NSQN model is in Australia, and a lot of the other bigger countries, like in the US, they've got all the facilities sort of lined up in big houses that are together, but we've got this distributed network where we're trying to share resources and work together. And something we're excited to try and do, through IAC this year is kind of be open for business to let people looking to qualify their space systems from other countries where their testing facilities might be even more oversubscribed than our own are, come here and test their things. So it's just another part, it's another thing that Australia can offer the international space community. But are there any more questions from the audience?
Hi, this is Calvin. Just a quick question to the whole panel. When you often get approached by SMEs or startups, do they usually have an agenda that they want to run with you, or sometimes they don't do enough research and you actually have to educate them to do that actual test in this case?
I can answer some of that. It depends on the kinds of clients you get. Saber's got a broad variety of different people at different levels of readiness, but we have had people at levels of readiness where they, the level of readiness of not even knowing that you need to do testing at all. So that's sort of a full end-to-end journey with them of helping them define their requirements, helping them figure out how those can be tested and validated and verified, and then collaborating with our experts and friends through the network, we're able to educate them as well on what that radiation testing regime looks like. So answer is yes, absolutely. We have people coming with no knowledge. And I think part of that's a problem of, the knowledge it's complex, it's difficult. But also, as mission design and mission support and mission assurance sort of engineers, that education is kind of our job, bringing them on and educating them. We shouldn't expect them to understand all of this stuff, but communicating the importance of coming to us in the first place, I think, is the thing we've really got to nail down.
Yes, my experience is that most of the time they come in with low understanding of what's needed, or even what they are looking for. But I think, as Josh said, the beauty of the NSQN and our facility is that we can provide the end-to-end offering. So literally starting from creating the question to solving the problem and analyzing as well the data and providing insights into the de-risking of the mission.
Yes, and that's something we haven't focused on. We very much focus on what the client wants. And so if it is a small SME that needs additional help, we can provide help. If it's an expert commercial in confidence, then we can train them up to use the facility. Basically, they bring in their own systems and they walk in, walk out, and that's it, basically. So we cater for everything from that perspective.
I think that's another Aussie benefit, is the amount of, as you were saying, coming off the ingenuity piece. I remember when we went and visited ANSTO, we were talking about all of the custom rigs that you guys build just to interface people's components with your facility. So if they come with a component, a lot of the facilities will build up the testing equipment if they don't have it, just to test that client's equipment, which is something that's pretty awesome and friendly, I think, about the Aussie testing community. Any more questions? Okay, I can do one final one. Oh, it is 10, but really quick one. How would you like to see the space qualification improve in the future? What's your hope?
My hope is that, covering all the questions that have been asked so far, so that people understand what qualification means, qualifying the hardware to hardware design, that they understand that to qualify you need to design it properly, and qualification has to be thought, the qualification process is expensive, it comes at the end, and you need to start thinking and planning about early. So really it's a matter of educating everybody to come up with a common understanding that qualification is not something you do at the end just to get your spacecraft in orbit. If you want it to succeed, you need to understand what you need to do, how you're going to do it, when you're going to do it, how much it's going to cost, all the who, what, when, where, why, how. And hopefully as the industry matures here in Space 2.0, we'll get that common understanding and it'll just be the way we do things.
Yeah, and I'd certainly like to see a very vibrant community, industrial community, where you have individual components and systems built, for space while they're in space and coming from space, basically, to have the whole circular economy of that aspect.
Thanks everyone for listening, and thank you to all our panelists. Another round of applause for all those great answers.